The idea of being able to keep things properly synchronized and avoid race conditions without doing locks was mentioned in earlier. There's actually an entire package in Java util concurrent. It's the atomic package, so Java util concurrent atomic, which has a whole set of different types that can be used to help do what are called lock-free programming. So all of these store values on them and allow you to modify those values in a way that is both thread safe but that does not use the full overhead of locks that you get with synchronized. And so I'd like for us to create, we'll make a new app called, we'll just call it atomic, how do I call it, atomic example. And we're actually going to go to a problem we've done a lot before, var count equals 0. And I want to look at the timing of this. So actually, to make my life a little bit easier, I'm going to create some little blocks here, because that way I don't have to redefine things or come up with different names for them. So we've seen before, if I have for I in 1 to a billion, and I increment my count here, we've seen that if we make this parallel by putting a dot par into this, we get the wrong answer, and it's because of the race conditions. And just to make sure you remember this, there we go. That's not a billion. That's, wow, 70 million. It's not even close to a billion. Yeah, that's way too small. Now, of course, if I get rid of the dot par, this gives me the correct answer. We've seen that we can make this correct also by synchronizing. So what I want to do is I'm going to add a little bit of code here. Val start equals system.nanotime, because I really want you to understand the cost of synchronization. And in addition to count, we're going to print out system.nanotime minus start times 1e minus 9, so we get how long this took in seconds. So I'm going to make one of these, which will be sequential. Okay, and that one gives us the right answer, and it does it in 0.6 seconds. Okay, so there's no parallelism there. Now, just for fun, we're also going to make a version that we'll call race, because this is the version that does it in parallel, but it does it with a race condition. And you'll notice it doesn't even speed it up dramatically. There's probably some randomness in this, but yeah, it appears to be running a little bit faster, but not much. Part of that is because this isn't taking all that long, but part of it is just because all of these threads are accessing the same point in memory, and we're getting the wrong answer. So let's copy this again, and let's, quote, fix it by using synchronization. So we're going to do atomic example dot synchronized. I put in the full name of the object there just to make certain that I know what I'm synchronizing on. And since there's only one atomic example, and we'll call this one sync. Okay, so on the order of 0.7 seconds, this time actually the sequential ran faster than the parallel version, and it got the right addition, or the right answer. Synchronize isn't done yet. Okay, I'm going to let that keep running while we work on our fourth version. This is the one that's going to use the new stuff. So we're going to create an atomic integer for our count. Now, the atomic integer does not have a plus equals 1 here. I might have to do fewer than a billion items if I want this to ever finish. What operations do we have? Well, there is an add and get. There is a simple get, a decrement and get, an increment and get. So for adding 1, that's the value that, or that's probably the best method. I could also use add and get and pass it 1, and that would add 1. And notice, and it also gets back the value from the increment. Yep, that synchronized version is definitely unhappy for the time being. We'll comment that, though we might just take our counts down a little bit, because I would like to see the atomic finish. In fact, I would like to, let's go ahead and we're going to take off 2 zeros. It will run 100 times faster, which for these first 2 means that the timing results will probably be fairly uninformative. There you go. Okay, so yeah, the race condition still loses out. Turns out that just incrementing by 1 is so fast to do sequentially, any attempt to parallelize it is going to slow things down. Even if you have a race condition, you're getting the wrong answer. But you can see the difference here between the synchronized version, which takes a full second, and the atomic version, which takes a half second. And those results are going to probably be at least reasonably robust. The atomics are running at twice the speed of synchronized. So if you can do things with atomic values instead of doing full synchronization, you should consider doing things with atomic values. The lack of locking gives you a lower overhead and typically will help you to improve your performance, which a lot of times when you're multi-threading, that's the only reason you're doing it. You're only going through the effort of multi-threading because you want better performance. Put in too much synchronization, you can kill your performance. What's worse, as we've also seen, too much synchronization can lead to deadlock. And the lock-free data structures, and the atomic values are guaranteed to not deadlock on you. So that's another reason why you should strongly consider using them. They're just going to be safer in that regard.